Okay, so let's start. Please quiet down. So this lecture will discuss UML. So the objectives are understand what is UML and how it can be used to model software systems, understand the essential features of UML, know some more advanced features, and appreciate that UML is a modeling language, but not a software development methodology. We'll discuss methodologies later in the course. So UML. So it's called Unified Modeling Language. It's a general-purpose visual modeling language for systems. Incorporates best practices in modeling techniques and software engineering. So best practice refers to the experience, the knowledge that people have summarized from many years of past experiences. They are shown to work well. It's experience-based. It is a software development methodology and process neutral. That is, it's independent of any methodology or process. It's just a language, modeling language, and nothing more. So it's an industry standard modeling language. Object-oriented modeling language. You learned object-oriented programming before. So with C++, you have classes, inheritance, and so on. Now this is an old modeling language. There should be a straightforward mapping to an old programming language. You can easily develop a code generator that generates C++ or Java code from a UML diagram. It's industry standard. That is, it's widely used in industry. If you go out to work for a software organization, chances are, if it's a large organization, you're going to use UML. It can also be used for non-OO systems. That is, you can design a non-OO system with some UML diagrams. Not all UML diagrams are object-oriented. Some of them, like sequence diagrams, use case diagrams, they can be used for any system. Only the class diagram and object diagrams are all specific. So the basic premise of UML is that, indeed, the basic premise of OO is that software systems can be modeled as collections of collaborating objects. So we'll elaborate on this point. So next, so UML essentially has 3 parts: building blocks, common mechanisms. Building blocks are the things, relationships, and diagrams. Things are the structural things. Relationships are how the things relate to each other. And diagrams, there are 9 types of diagrams in UML. So mechanisms include specifications, that is textual descriptions of an element, adornment, that is additional annotations for describing the details of each modeling element, common divisions, that is particular ways of thinking about the world. We'll discuss division between classifier and instance, for example. A student is a classifier. Each one of you is an instance. So that's the difference. And also interface and implementation. That's also another division. Extensibility mechanisms, that is ways to customize the modeling elements for specific needs. Because the realistic software applications are very diverse, ranging from flight control to your cell phone. But you have one common language. How is that possible? The key answer lies in the extensibility mechanisms, where you can define your custom notations to customize UML for your particular application domain. architecture, that is the high-level structure of the system. So there are 5 views. Use case view captures the basic requirements for the system. For example, for the course registration system, register for a course is a use case. Drop a course is another use case. Logical view captures the vocabulary of the problem domain as a set of classes and objects. Perhaps in the logical view, you have student, professor, registrar, courses. These are logical entities in your system and how they're related. Process view refers to the executable threads and processes. Perhaps your final system is a multi-threaded system with 5 threads. Implementation view refers to the source code, the files, and the directories, which file for describing which aspect of the system is put in which directory. So deployment view refers to the physical deployment. That is, for your course registration, perhaps you need a powerful server, central server, to deploy the server database part of your application. And perhaps you don't need any client-side software. You just need a web browser for the client. So all these views describe the same system from different perspectives. So first we'll discuss building blocks. So why build models? So models succinctly describe reality. That is the abstract reality. So for example, a model airplane is just like an real airplane, but it's more abstract. It's missing a lot of details. They show essential details and filter out non-essential details. So that they allow us to focus on the big picture of the software development, i.e. programming in the large, as we mentioned before. This is the key difference between software engineering and programming. Software engineering can be viewed as programming in the large. And to better deal with the complexity of software development, because human mind has limits on how complex it can grasp. So by abstracting the perhaps millions of lines of source code into some visual models that abstract out all the details and only leave the essential parts, it helps humans to understand a large software system better. Results in better understanding of requirements because instead of vague natural language English requirements that I gave you as part of the course, you need to design a UML-based requirement specification document which is much more precise because UML is quite formal. Cleaner designs and more maintainable systems. It's more maintainable because it's easier to understand. You can, if a new developer comes in the group, you can show him the UML diagrams, and he can quickly grasp the overall architecture of the system. So why objects? So object more accurately reflect the real world in the model, thereby reducing the semantic gap between reality and a model. So here's the reality. It's a person who works for an organization, perhaps a company, and owns a car. So there are 3 things in the real world: an organization, a person, and a car. Now, typically before OO, people used file-based systems. Perhaps organization information is captured in a file, perhaps an Excel document or Access database. and the car information is captured in another file. So in a city, you may have many companies and many cars and many people. So how do you capture the person? So really, you need to capture the fact that a person works for an organization and owns a car, but this thing doesn't really belong in any of these two files. It's really something that sits in the middle and correlates these two files. So there's a semantic gap involved in between the real world and the actual computer model of it. So objects OO is designed to remove the semantic gap. So just like in the real world, you have three things: organization object, car object, and person object. And a person works for an organization and owns a car. So he can also own multiple cars or work for multiple organizations. He can take multiple jobs. In that case, you can annotate the association with multiplicities to show organization perhaps has 200 people and one person can work for two organizations, for example. So you can see it's very intuitive. By using objects to model the real world, you have a direct correspondence between the model and the real world. Objects help to localize changes to the model. That is, so if a person sells his car and buys another one, then you just need to update the association between person and car. Perhaps delete some links and add some new links. Instead of in the previous file-based model where you have to go in and modify multiple files. So we model reality as a collection of interacting objects. So there are multiple levels of abstraction in OO modeling. Conceptual level, where we construct a problem domain model. That is also called a requirements model. So this model is in the problem domain. That is, you only consider the application domain concepts. There are no software concepts, no programming concepts, computer science concepts. It's only in the problem domain. It's intended for communication between the developers and your client. So we do not consider any aspects of implementation. Focus on identifying concepts in the problem domain. So, for example, in the course registration system, the problem domain model would consist of obviously course, students, professors. These are the identifying concepts, key concepts. There are maybe some secondary concepts like the university. It's a concept. The classroom is another concept. So these are the problem domain model elements. Design model is the second stage model, more concrete and less abstract, where we construct a solution domain model, i.e. a software model. At this stage, you design the interfaces of objects, but not internal aspects. There is no implementation yet. You just describe what interface this object is supposed to provide to the other objects. For example, the course object must provide a register method as its interface. But you don't specify how this method is actually implemented behind the interface. That's for the next stage. So this focus here is on how objects interact in the solution domain. That is how the software entities interact So implementation level is when you actually implement the solution domain model. So the solution domain model at design level is just a bunch of UML diagrams. They're not executable. They're not runnable. Implementation level, you actually write C++ or Java code, or you can use some automatic code generators to help you generate a partial code from your design models, and then you fill in the details. In this stage, you consider all details of objects, external and internal. External refers to the interface, internal refers to the implementation, because you need to compile it and run it. So here, the focus is on how to code objects, that is actually implementing each interface method. So same old concepts can be used at all levels to build models. That is, for the course registration system, the same concept persists throughout the entire process. So you start from conceptual level. You already consider students and professors, and you go down to design level. You have the class diagrams for students and professors, and finally to implementation level, where you actually implement the internal details of student-professor objects. So the same concepts persist across all levels. So the distinction between objects and classes. So I've been talking about objects so far, but sometimes it's more accurate to refer to classes. So the difference is that object is an instance. It is a physical or abstract thing with crisp boundaries and meaning, which can respond to a request for an operation. So here's the object. An object, Fred's bank account. It's a concrete thing that exists in a bank. So it may have 3 operations. That is, its interface consists of 3 operations for the other objects to call. So a balance returns the current balance of the account. Deposit takes an parameter amount and puts this amount of money into the account, and withdraws this amount of money from the account. So the interface describes the operations with which an object can perform. So suppose I'm another object, say I'm Fred, I can invoke this object's balance method to get the balance of the account. So it says here, which can respond to a request for an operation. So the request arrives from outside, from other objects, onto the interface of this object, and then this object does some internal calculations that's hidden from the outside, and eventually returns something back to the outside object. Now, objects may also have, besides interface, it may also have properties. So for this object, it may have a balance attribute as its property, $2,000. And in addition, most objects have this internal identifier attribute, 167845565. So this is often called OID. That is a unique internal hidden identifier that distinguishes one object from another. It's typically not shown to the programmers to the outside, but it's typically present internally. So if you work with C++ compiler, you'll notice that every object has a hidden OID inside of it. So, and behavior is the code behind the operations. Remember, the operations form the interface, and there are implementations or behaviors behind the interface. So, information hiding. So, I alluded to this earlier. So, objects interface provides encapsulation and abstraction, and that's achieving information hiding. So, every request from a user to an object, or from one object to another object, must go through the interface. It cannot bypass the interface and go directly into the implementation. That's why you have the public-private keyword in C++ to enforce the interface. If it's a public operation, you can call it. Otherwise, some other objects cannot call this any private operations. So the user could be a user interface element. For example, could be a button. If you click on it, it invokes some operations on some object. So this information hiding hides the implementation behind the interface, so that an object provides a public interface, but a hidden private implementation helps promote modular development. That is, anytime you need to change an object's internal implementation, you can just change it without affecting the other objects in your system. So as long as the interface is agreed upon, you can just develop the work and give it to multiple developers in the organization, and then integrate them together later. So the development is modular because each team, each person can work relatively independently from each other as long as the interface is well defined. So class is a description of a group of objects that have common state, behavior, relationships, and semantics. Semantics, this word, it means meaning. So something semantics means that what does it mean? A class provides a template to create objects, like a factory for objects. It's like a stamp, right? You have one chop, and you can stamp out many stamps. So it's a template. Any object created from the template is an object of the class with the identical behavior, relationship, semantics, and all that. So class is a classifier, object is an instance. As I said before, for example, student is a class, it's a classifier. Each one of you, Fred, Tom, Jim, Sam, each one of the individual students is an object. It's an instance of student. So a good class should capture one and only one abstraction, should have one major theme. So this is the really part of the class design. In this course, in this project, you will design a class diagram for your problem domain. So you can make a class very general and very abstract, or make it very concrete and very fine-grained. It's your design decision. But in general, you should try to keep the class focused on one abstraction. So, for example, if you have a car class, that's one design, or you can have a more fine-grained design that is, say, a SUV or a sedan or a truck. Which abstraction level is better depends on your application domain. So if you are modeling a person owns a car and works for a company, for that example, perhaps a car class is enough. But if you're modeling a car repair shop, perhaps you need to create more fine-grained classes to capture the differences between different cars. So a class should be named using the vocabulary of the problem domain, so it's meaningful and traceable, especially to your client, because this requirements document, including the class diagram, is supposed to be shared between the developers and the client. So you should try to use the problem domain vocabulary, not any of the computer science vocabulary. So attributes are description of data values held by objects in a class. So each attribute has a name which is unique within the class but not across classes. So for example, a person may have 3 attributes: age, weight, and name, right? And a car may have many attributes: a color, weight, cost, make, model, etc. So the name of the attribute must be unique within the class. That is, a person must have only one attribute called name. Well, that's a little confusing because the name really refers to the name of the attribute. So the person must have only one attribute called age. Well, a car can have also have an attribute called age, but there cannot be two age attributes within the same class. That's what it means to a name must be unique within the class, but not across classes. So type specifies the domain of values. String, integer, many, etc., from which an attribute can take its values. So could be continuous or discrete. Discrete attribute like sex, male or female, color, red, green, blue. Continuous like salary, from 10,000 to 20,000. Name, where you can really have any name, any combination of letters, as opposed to continuous, where you must choose from a fixed set of values. And visibility indicates who can access the attribute's values. Could be public, private, protected, and packaged. So this should look familiar to you. This corresponds directly to the programming language concept in C++. Except the package concept perhaps is unique to the UML, where you can develop your classes into multiple packages, and some attributes may be only visible to classes within the same package, but not to some other packages. So a public is accessible to any other class. Private is only accessible to the class itself. And protected is accessible to the class and any of the subclasses of this class. We'll discuss subclasses and inheritance later. Initial value is an optional attribute which specifies the attribute's initial value. So that is, when you create an object initially, for example, in C++, you have new. Without assigning any of the values, what is the default initial value? Multiplicity specifies the number of simultaneous values. So telephone number, for example, you may have 2, your home phone and your office phone, or 3 plus your mobile phone. So you may specify a default of 1. Changeability, which specifies whether the value can be changed. Could be no constraint, or frozen, or add only. No constraint means that it can be arbitrarily changeable, and frozen means that the value may not be changed after it's initialized. For example, for a person class, the birth date should be frozen. Add only, that is, additional values may be added to a set of values. So, for example, you may have a phone number attribute. You may specify it as add only, that is, you can add more phone numbers to this attribute. You may have base attributes versus derived attributes. For example, base attribute birth date is stored in the class, while age is a derived attribute. That is, you can obtain age by a simple subtraction if you have the birth date. So it is not stored or permanently, but is derived on the fly as requested. So the UML notation, so first of all, you're not required to know this syntax. It's just for information only. So the overall notation is a stereotype that we'll discuss in the future. So it's additional annotations to customize your class for a particular application domain. We didn't discuss it here. Visibility, which is plus, it means public. Minus, it means private. Name, and parentheses, multiplicity. For example, telephone, parentheses, 0.2, it means that you may have 0 or 1 or 2 telephone numbers. A type expression, that is a string, or money. Money is a type. And equals initial value. So, for example, this guy's size is of type area. Its initial value is 100,000. And then parentheses property string could be frozen, could be add only, could be something else. The only name is mandatory in UML. All the other attributes can be omitted. So here, salary is a private attribute with the minus in front. Colon money means that it is of type money. And parentheses greater than 0 and less than a million. This is the range for the salary. Notice that the type expression could be something that you define like money. It doesn't have to correspond to any programming language type, like double or int or short. At this stage, at the requirement stage, we don't care how you implement it. We only care about this represents money. If you implement it with a double or a floating point, that's not of our concern at this stage. So operation. So we have discussed attributes. Now we turn to operations. Operation is a function or transformation that may be applied to or by objects in a class. So a company class may provide operations like hire, fire, pay dividends, hire an employee, fire an employee, pay dividends to your shareholders. All these are operations available in the interface of the company class. A course may provide register or waive prerequisite. So notice that the operation could be applied to or by objects. So register is applied to a course, while hire is applied by a company to an employee. So it's a design decision as to whether you want to put the hire and fire operations in the company or in the employee class. Both are okay, but their usage is different. So an operation is invoked by a message sent to an object and has the following properties. So the message is really a very conceptual level concept, abstract concept. It doesn't correspond to any network package. It's just the abstract message. In reality, it's often implemented as a method call. So operation signature, that is name of the operation, also called the selector in the old jargon. So it selects among multiple operations on the same object. Names and types of arguments and type of the result value. So that's the operation signature. Visibility could be a public, private, protected, or package. This is the same as attribute visibility. Side effect, that is, if the operation, if the execution of an operation changes the state of an object. So, for example, a query operation has no side effects. It doesn't change the state of the object. For example, the bank account has a state, it's balanced. So if you call get balance operation, the balance is going to stay the same. But if you call withdraw or deposit, these operations have side effects. They change the balance, change the state. So method is an implementation or the code behind an operation, code for the operation. So operation is visible in an object interface. Method is hidden. So operation is a classifier. Method is the instance. So why do we say that? Because an operation may have multiple implementations, multiple methods behind it. So we'll show it next. So a so-called polymorphic operation, where, for example, you may have a class account with an operation pay interest. Maybe it's called periodically every month. So for a savings account and for a checking account, you may have different interest rates. So your method for implementing the pay interest operation is different for a checking account or savings account. Therefore, you have this separation, distinction between the classifier and instance, operation and method. So we'll discuss generalization and specialization next very quickly to describe how you can override methods in subclasses by providing a different method for the same operation. Dynamic binding is to choose the methods to execute for an operation based on the object's class. That is, especially in if you learned C++ programming, you know that if you call an operation on an object, and this object may have subclasses or superclasses, so with different definitions of the methods behind the operation, then which one is called is based on the actual type of the object. It's called dynamic binding because you can't know it at compile time. You can only know which method is invoked at runtime. It's dynamic. So UML notation for operations, again, you're not required to know the syntax. So basically, it's similar to the attribute notation where you have a stereotype, which we did not discuss: visibility, public, private, protected, name, parentheses, parameter list, return type, and property string. So parameters can be in, out, or in, out. So in is when you pass by value. When you pass it in, you cannot change it. So if you pass something by value, you can change this variable in your method, but it doesn't affect the variable outside of the method. If you pass it by reference or by pointer, then you can modify it. That's why it's called out and in out. Property string means that if it's a query, its query means that it's a query operation. It has no side effects. If it's false, and then it's likely to have side effects. It's polymorphic means that it's redefined in the subclass. So you must be careful as to which one you invoke. It's false means that it cannot be redefined. It's final. It cannot. It's fixed. Concurrency means that sequential, guarded, and concurrent. So that is, if you have multiple threads in the system, they're invoking multiple objects. If a operation is sequential, it means that the caller to the operation must ensure that only one thread is active at any one time while calling the operation. If it's concurrent, it means that multiple calls can happen concurrently without any restrictions. This can be achieved by using mutex locks, as you learn in your operating systems course, to protect shared data. Or guarded means that you can call the object from multiple threads simultaneously, but only one is allowed to execute at any one time. Other calls are blocked. So this really corresponds to using a huge lock to lock the entire operation from the entry to exit. So graphical notation of the class diagram, you have 4 compartments. Class name is on the top. Attributes compartment contains the class attributes. Operation compartment contains operations and extra. It's used for extra annotations. So here's the one concrete class with 3 compartments. Name, bank account, 3 attributes, account number, amount, and count, and a bunch of operations. So we have a special type of attribute called a class attribute. This count has an underline beneath it. It means that it is common to all objects in the that belong to the same class. It counts the number of bank accounts, number of currently active bank account objects. Obviously, you cannot store it in any one of the objects. It's not an object-specific attribute. It's a class-wide attribute. And class operations create an account with the account number as the parameter. Increment count, that is, increase the number of bank account objects, and get count means get the total number of bank account objects. So you can see that increment count is a private operation. Obviously, it makes sense, right? It should be only called by the create operation. You cannot increment the count without actually creating an account. That would be wrong. So the difference, as you can see, all these are manipulating the class attribute, that is the total count of bank account objects, while each one of the object attributes, like account number and amount, they are specific to each object. If you have 10 bank account objects, you have 10 different amounts, but you have only one count, which is equal to 10. So visibility, private, public, protected package. So classes, by abstracting a collection of objects and representing them as a class, the complexity of developing a system is reduced. It becomes easier to understand the system, to understand only the classes, not the individual objects. That is, if I design the cross-registration system with a student class, I only have to know that a student has a student ID attribute, a age, a sex, a name attribute. So every one of the student objects will have the same set of attributes and operations, so that we only need to understand the class when we are trying to understand the software system. And makes it easier to specify the system, to define and store common definitions only once. You don't have to specify any attributes for each individual object, which may run into thousands. or millions. So the choosing the appropriate class is an important design decision that helps promote modular development. When you design classes, you need to design the operations that serve as its interface. A proper choice of the operations as its interface is instrumental in promoting modularity and encapsulation. So I will discuss a lot about class diagram design, and you will have to do it for the project also. Okay, so see you next time. So next class I will be traveling, so Professor S.E. Chan will teach the class on Monday. I'll be back on Wednesday. Okay, I'm sorry. I got the time confused because, yes, this is the first time that this class has 2 different time slots on 2 different days. So it's easy to get confused. Sorry. Okay, let's continue. Okay, so thank you for the reminder. Okay, generalization. So generalization is a relationship between classes of the same kind. So look at this bank account class. You have account type as an attribute to distinguish between checking account and savings account, right? Therefore, if it's a checking account, then you have balance, deposit, and withdrawal operations available. If it's a savings account, you may have additional pay interest operation available. Suppose the checking account doesn't pay interest. So you may have specific attributes that apply only to a checking or savings account. So service charge is only applicable to a checking account, while interest rate and pay interest only apply to savings accounts. And then account type is an enumeration type, whether checking or saving. It's also called a discriminator. That is, to look at an object, you see the account type attribute, and you know whether this particular object is a checking or savings. So an attribute of enumeration type that indicates which property of a class is being abstracted by a generalization and specialization. So what does it mean? So instead of the previous class diagram, we can redesign the class diagram by pulling out 2 special subclasses into their own class. Checking, which has the service charge attribute, and savings, which has the interest rate and pay interest attribute and operation, in addition to all the attributes and operations in the base class, or also called superclass. So that is, all the attributes and operations here are inherited by the subclass. So this is called a top-down design specialization. That is, you start from this particular class, and then you pull out the common one into a base class, and the specific ones into the subclass. So now notice that checking has 3 attributes. 1 service charge plus the 2 in the base class that's inherited in the superclass. Savings has 3 attributes and 4 operations. So also can also be applied bottom up. That is, you may have a bank account class, you may have a credit card account class. Now, you see that there are a lot of similarities. Account number and amount and balance get balance, and add charge is specific to credit card account. Make payment and charge interest. So these two attributes are common, so you can pull it out, and this operation is common to both classes. So you can pull it out into a superclass just with the common parts. Therefore, you reduce the size of the two subclasses. So this is called generalization. So remember, top-down is specialization and bottom-up is generalization. They refer to the process of designing the class diagram. So after you design it, it doesn't matter anymore. But while you're designing it, you can start from the bottoms, from the concrete classes, and pull out the common parts as generalization, or you can start from one class and divide it up into multiple classes. That's specialization. This is the superclass, and bank account and credit card account are the subclasses of the account superclass. At the same time, bank account itself is a superclass for the subclasses of checking and savings. So a class can both be a subclass to some superclass, at the same time still be a superclass for some other subclass. So this thing can be a whole tree that's many levels deep. So inheritance is the assumption of properties by a subclass from its superclasses. So we extract common attributes and operations and put them in a superclass and inherit them to subclasses. Therefore, you reduce redundancy in your class diagram by having this common superclass. The benefit is that properties and behavior are only defined in one place, that is in the superclass. You reduce redundancy of descriptions, promote reusability, and simplify modification of descriptions. That is, if you want to change the common attributes of operation, you can only need to change it in the superclass. It's automatically inherited by the subclasses. Otherwise, if you have it in two different places, then you need to go in and change each one individually. So having the superclass helps you to modularize your changes. So an object of a superclass can be substituted with an object of the subclass. That is, any time a superclass is applicable, you can always use a subclass in its place, but not vice versa. So, for example, for the bank account example, anytime a bank account object is used, you can always use the checking account in place of it, because a checking account is a bank account, but not vice versa. If you have some situation where a checking account object is required, you cannot substitute in its place a bank account, because the bank account may not have the checking account specific attributes and operations. So that's the substitution principle. So a subclass may add new properties, that is, attributes and operations. For this example, checking subclass adds service charge attribute, and savings adds interest rate and pay interest attribute and operation. And you can override method in a subclass. Notice I said method. I didn't say operation, right? So you must keep the same operation name, yet you override the internal implementation of the operation. So This is called single inheritance because a class has one parent only, one superclass. There may be multiple inheritance. That is, you may have a hybrid account type called checking savings account, which has really you can write checks from it, and you can get interest from it. So I think the bank accounts you open at the banks in Hong Kong are typically hybrid accounts. Has a mix of both characteristics. So then you run into a problem because suppose checking account subclass overrides the withdrawal method. That is, the withdrawal operation is the same with the same signature, but the internal implementation is changed. Now, if the suppose in the superclass withdrawal, if you try to withdraw an amount more than your balance, you simply fail, return an error message. But in the checking account subclass, you may let the withdrawal succeed, but at the same time charge a service charge for overdraft. Then the savings account subclass inherits the base class's withdrawal method, while the checking account base class subclass overrides the withdrawal method to have a service charge and overdraft. Then, if the checking savings account inherits from both checking and savings, which method does it inherit? Right? The operation is the same, but the method is different in the two account types. So this is really an ambiguity that must be resolved in an application-specific basis. So that's why multiple inheritance, although it is allowed in most programming languages like C++, it is generally discouraged for good programming practice. So conflict resolution can be by user-defined order. That is, the user may say, okay, always prefer the operation methods in the checking to the savings. So anytime you have a definition, different definition, always choose the one in checking in preference to the one in savings. For predefined order or redefined names, that only applies to attributes. You cannot redefine the name of an operation. So you can only redefine the method, that is the implementation of the operation. So there's not a general mechanism for resolving conflicts. So conflicts occur when an operation or attribute can flow to the same subclass through two different paths. One from one inheritance path and one from another inheritance path. Then you need to resolve the conflict. Obviously, if you disallow multiple inheritance, this problem goes away, right? So, so here's an example. So you have a person who has two attributes, name and Hong Kong ID. A student inherits from person, an employee inherits from person, and a TA is a student. He's a PG student. At the same time, he or she receives pay from the university, so he's also an employee. So he inherits from both the student and the employee. So from the person superclass, the student class gets the name and Hong Kong ID, and eventually get passed down to the TA subclass. Also, name and Hong Kong ID get passed Then this branch from the employee to the TA subclass. So these are fine because name and Hong Kong ID are common to both student and employee. But what about ID? The TA subclass gets the ID attributes from the student superclass and also from the employee superclass. So they have different meanings, right? ID in the student class refers to the student ID, while the ID in the employee class refers to the staff ID. So, so which ID is the attribute in the TA class referring to? So that is a conflict which has to be resolved manually by the user or by redefining the attribute names. Perhaps you rename it as a student ID and rename this ID as staff ID. So another example, vehicle. Land vehicle inherits from vehicle. Water vehicle inherits from vehicle. Now, each one has a size attribute. That is, but they have different meaning, different semantics. Land vehicle size refers to its weight, how many tons this vehicle weighs. Well, the water vehicle size refers to its water displacement. So now you have a car that's a land vehicle, inherits from land vehicle. Boat is a water vehicle. You may have an amphibious vehicle, which can run on the road and also in the water. So now you have another conflict where an amphibious vehicle gets the size attribute from two different inheritance paths, from two different parents. So again, this conflict needs to be resolved by renaming the attribute or by user-defined resolution. So multiple inheritance can be useful. It has greater power in specifying classes. At the same time, conflicts are a real issue. So it's generally discouraged, both in modeling and in programming. In particular, for your project, you should not use multiple inheritance. So a class can be abstract. That is, it has no direct instances. In UML, it is shown as the italic font in the class name. So for example, if you have only two types of accounts, checking or savings, there is no other type of account. Whenever you have a bank account, it's always one or the other. Therefore, it doesn't make sense to have the account object that is not checking or savings. Therefore, accounts can be put into modeled as an abstract class. You never directly create account object instances. You always create only checking account or savings account instances. So it's useful for modeling as a container for definitions. It may contain all the common attributes and operations like balance, get balance, withdraw, deposit, but you cannot create instances of the abstract class. So this is actually in C++. You have the abstract keyword. If you are aware of it, if you specify a class as abstract, then you cannot do a new class name later. So operations may also be abstract. That is, no method specified. This particular operation only has a signature with no concrete implementation. It is shown in UML with the italics for the class name and for the operation name. So why would you want to have an operation without a method? What use of it is it? It may be useful in abstract classes where you cannot create this account object directly, but you can inherit from the account class and define the operations method within the subclass, right? So in C++, you may heard of pure virtual methods, right? Pure virtual method is when you add equals 0 at the end of the operation signature. It means that this particular method has no code in it. You cannot call it. It is only intended for redefinition by your subclasses. So coverage refers to how the subclasses relate to each other. So, for example, a tennis player and a soccer player, they both inherit from the player superclass. They are overlapping because a person can be both a tennis player and a soccer player. So that's the kind of a Venn diagram. If you learn set theory, you know Venn diagram, where you have circles indicating sets, and their intersection indicating these are the people who are both a tennis player and soccer players. Disjoint is when a superclass object is a member of at most one subclass. So account, you may have a personal account or a business account. But any account can only be one or the other. It cannot be both personal and business. In this case, there's no intersection between these two sets. That's disjoint coverage. Complete is when for example, university students, you may have two subclasses, undergrad and postgrad. So these two put together, they cover the entire university student population. There's no one else left. That's who's a student, but not an undergrad nor a postgrad. You must be one or the other, and there's no third alternative. So this is complete. At the same time, this is also disjoint. Incomplete is when some superclass object is not a member of any subclass. So, for example, tree, you may have oak tree, elm tree, and birch tree. Obviously, there are many other types of trees other than the three here. So it's incomplete coverage. So you may have multiple combinations, like a course could be a UG course, that could be a PG course. At the same time, it can be cross-listed as both a UG and a PG course. So it can be overlapping, and it's complete because a course must be either one or the other. It cannot be any. There's no course that's not a UG nor a PG. So notice here the intersection for HKUST. There's really no courses that are both UG and PG courses. Well, some UG students can take some PG courses, but courses are listed as either UG or PG. So it's not overlapping in the case of HKUST, but for some other universities, some courses may be cross-listed. So in that case, it's overlapping. So again, to decide on the coverage, you need to consider application domain. That's why you need to communicate with your client to discuss the semantics of your application concepts. For this overlapping or non-overlapping is specific to each university. Therefore, there's no one true standard correct answer. So player, it can be a tennis player or soccer player, so it's overlapping and incomplete. It's overlapping because it can be a both tennis player and soccer player. It's incomplete because you can be some other player, like a basketball player. disjoint complete. So undergrad, postgrad, they're disjoint and they're complete. Disjoint incomplete is when oak, elm, and birch, where a tree can be either one of the three, but cannot be both oak and elm, right? At the same time, it is incomplete because there are many other types of trees. So here's the a question for you. Look at this inheritance diagram where you have a payment zero class. Payment could be a cash payment, a credit card payment, or a debit card payment. The coverage is overlap incomplete for disjoint. So what do you think? Any volunteers? Since you're sitting in the front row, so what's your opinion?
What kind of payment is it? Can I pay beside this out of the three, let's say ultimate cards or other check or?
Yeah, that's a very good question. The student asked, can you pay with octopus card or check or any other payment methods? So that's a very good question because it's not shown in the particular class diagram. That's the information you must obtain from your client. Therefore, whether which one it is really depends on the particular client, the particular company you're working for, the system you're developing for. So if that's the only three type of payments it accepts, then it's complete. If the company accepts checks, then it's incomplete, right? So this is really a trick question because you must obtain this information from company policy, right? So, and also, is it disjoint? Well, it may be disjoint. But if a particular company allows you to pay part cash and part credit card, then it is overlapping. So the answer is it depends on the organizational policy. So customer can be a buyer or a seller. So the generalization above. So this is really a question for the last semester's course project, where you're supposed to develop a online auction system like eBay, where a customer can be a buyer or a seller. So, and also he can be both a buyer and a seller. So it is overlapping, and it is complete because there are only two types of customers: buyer and seller. They are customers to the eBay website, but the buyer is the customer of the seller, but that's not the meaning of the customer here. The customer means the website's customer. Again, from last semester, auction could be a regular auction or reserve auction. Reserve auction is when the seller sets a reserve price. So if the auction ends and reserve price is not met, the item is not sold. So this is disjoint, and it is incomplete because in the problem description we have another type of auction called Dutch auction, which is not shown in here. So you should be happy for this semester's course project because last the auction project was really hard, and students it took them a lot of time to develop the auction. That's why we had 7-person teams last semester, but this semester the project is much simpler. Therefore, we have 5-person teams. Still, it'll be a lot less workload than last semester. So, So stereotype is a modeling element that is a subclass of an existing modeling element. So allows the object model to be dynamically extended. So I mentioned stereotypes earlier to customize UML for your particular application domain. Because UML is just one language. You have many, many very diverse application domains. The way you address that issue is to add stereotypes to add modeling power to extend your object model. So, for example, we'll later discuss this in more detail. So, you may have a three-tier architecture where you have a database with the bank account object information is stored, and order form is the user interface element, and pen tracker is this control element, which means that it really coordinates the accesses, all the operation calls from the boundary to the entity must go through the control. It acts like the conductor of the whole system. So these little things here, control, boundary, and entity, these are called stereotypes. By adding the stereotype to the class name, just above the class name, you specify additional information. That is, you're saying this guy is an entity class. It means that it belongs to a database. This guy is a boundary class. It means that it belongs to the user interface, to the GUI. And pen tracker is a control class. It means that it belongs in the internal details, internal of the software system, not visible to the user. So don't worry if you don't really get it now. We'll discuss it in a lot more detail. So you may have special icons for each stereotype to improve modeling clarity. So you may have a ball sitting on the ground, indicating that the bank account is an entity class. It means that it's a concrete entity. It's something that can be put on the ground. It's something that you can grab. Well, this boundary class stereotype may have this shape here means that it's a boundary. That is, anything from on the right side is the inside of the software system. Anything on the outside is the human user or some other external environment. So that's the boundary. And the control is this circle with an arrow. It means that it goes round and round. It means that it's coordinating different things. Of course, all these icons are just conventions. You can always define your own icon. So, links. So we have these objects. So, for example, in the course registration, you have persons, professor name, James Kwok, me, Fred Lachowski, courses 327, 337, organizations, HKUST, Boeing. Now, these are not isolated objects. They talk to each other, right? So links are used to indicate relationship between object instances. So Zonghua Gu teaches Comp 211, and Zonghua Gu works for HKUST. So these are links. Teaches works for are the names of the links. So a link allows one object to send a message to another object. The message is a conceptual message. It can be a method call, or it can be a network message. Could be a TCP/IP packet. Could be anything. We don't care at this stage. At this stage, we only care about you can send a conceptual message between two objects. So association is a description of a group of links with common semantics. So that is a person class and a course class, they have an association called teaches. Notice that association is between classes, while links are between objects. So association is a group of links with common semantics. It means common meaning. So association is a classifier, a link is an instance. Again, you see this classifier instance distinction. Remember, so class is a classifier, object is an instance, operation is a classifier, method is an instance. Again, here, association is a classifier, link is an instance. Another association is person works for organization. So, of course, in the class diagram, you shouldn't duplicate a class. The notation should be a class should have an association to organization at the same time to a course with a teacher's association. So this thing is called a class diagram. It's the most basic one, but that's the basic idea. So any of the associations, when you turn into objects, they turn into many links. So person teaches course, one association may turn into 5 links in here. So conceptually, associations are bidirectional. That is, you can navigate from person to teaches to courses through this association, and also in the reverse direction. So you can look up what course a person is teaching this semester, and at the same time you can look up what person is teaching this course, right? So unless you have a arrow on either end, then it's a one directional. But without arrows, this is a bi-directional navigation of associations. Okay, I think I'll stop here. So see you next time.
请 Group 101的